I'm Zoltán Lehóczky, as we have probably also heard, and I'm from a company called Lombik Technologies. We have been here a few times. Actually, I'm very proud that I was there with my friend and business partner Benedek on the very first GPU day, 11 years ago. So that's quite a heritage. There are two colleagues of mine who worked on this project who can't be here today, David from Lombik as well, and Ernő Dávid from Vigner. But let's see what we actually have to figure out here. Just a bit of interaction before anything else. Lombik is actually mostly a software development, a web development company. We work with open source Microsoft technologies, .NET mostly, and mostly on web projects with a content management system called Orchard. Now, Orchard is an open source software. We are also very much focused on open source. And during these endeavors, we work with companies like Microsoft itself, or Live Nation, or institutes like the Smithsonian Institution. But when we are not doing some web development, then we are doing some research and development, like on our Hastlayer project. But before talking about that, let's talk about you. Let's suppose that you are doing some number crunching, all right? And by number crunching, I mean some computations, some heavy computations in the field of, for example, scientific computing, of course, or something in the field of machine learning or AI, or image or video processing, which are highly parallelizable computations, or computer vision, which is tightly related, or anything with data compression. Now, if you have some computationally heavy algorithm or application here, then you probably want to make it faster. And to make it faster, you have a couple of steps, a couple of general steps to take, which is probably familiar to everyone here who has written a bit of code. First, you can profile and optimize it, so figure out what is slow and make it faster. But let's suppose that you have already done that. Secondly, you can also parallelize it to make it multi-threaded or use multiple computers even, but let's suppose that you have already done that as well. And of course, you can use faster hardware. In the cloud, you can scale up fairly quickly, or you can use more hardware, more servers. You can also scale out. Now, you have done all of that. What is it that remains? Well, everybody knows the answer because we are on GPU day. Of course, you can use some heterogeneous computing approach. So hardware accelerators like GPUs or FPGAs. Now, let's talk about that last part, FPGAs, a bit more. Probably most of you are familiar with them, but for those who aren't that much, FPGAs, or field programmable gate arrays, are pretty much computer chips that can behave like any other computer chip, within limitations, of course. So they can be dynamically rewired on the fly to mimic some kind of other chips to do some computations. This is cool, but why do we actually want to use FPGAs? We want to use them as compute accelerators because they have some unique benefits compared to, for example, CPUs and GPUs. And here is how they compare. This is just a totally non-scientific, very rough comparison, just to give you an idea. All of this highly depends on, of course, the specific application and the specific devices. But let's talk about the parallelism first. So how many things you can compute at the same time? With CPUs, the first chart and the bar in blue, I would say that they are on the lower end here. So in a CPU, you have something like maybe 8, 4, 8, 16, perhaps 32 cores, but that's about it. GPUs in orange, on the other hand, are on the other extreme. They're highly parallel computing devices, highly parallel architectures with thousands of little processing cores. And the FPGAs are kind of in between, although they're not cores on an FPGA, although that depends on the specific device. Now, what about the complexity of programs you can run on these? So, all right, we have parallelism, but what can we actually do with these devices? And CPUs win here because if it's software, you can run it on a CPU. GPUs are on the other end, but on the lower end, I would say here, because the programming model there is much more limited. And FPGAs are kind of in between again. All right, so still, why use FPGAs? Because of the last thing, power efficiency. And power efficiency is something that, of course, matters in mobile devices like this laptop, but also if you do a lot of computations in a data center where power consumption and subsequently air conditioning is the major cost factor in actually running a data center. Because FPGAs are very power efficient. The reason there is because when you use an FPGA, it only computes what you need to be computed. There is no operating system to run, no other software. There's not even an instruction set for a processor because everything is hardwired. Okay, that sounds great, but what's the catch? And the catch is that utilizing FPGAs is hard because it's not easy like software development, but it's hardware development. It's super low level. You have to think in terms of wires and logic gates and clock cycles. It's very hard, very slow. Even if you are experienced, it's a lengthier process than writing a program. But with Hastlayer, we intend to bring this down onto the software development level. Because what is it? Hastlayer is pretty much a tool that takes a computer program and converts it into a piece of FPGA logic. You could also say that it takes a computer program and creates an equivalent computer chip out of it. And not just any computer programs, actually. We are talking about .NET. You know, the .NET platform is an open source cross-platform programming environment. It's not a programming language. It's a platform that supports many programming languages. The most popular one is probably C#, but also C++ and functional languages like F# or scripting languages like Python. So all in all, we want to have the computing benefits of FPGAs for all of us software developers. That means that if you have a highly parallelized application, then you will get a performance increase. Secondly, you get a power efficiency increase, so you can compute more stuff with less amount of power. And thirdly, it's still programming as usual. So all cool. Now let's see it in action. And I'm now switching over to Visual Studio to show you a bit of code. This is some C# code here, which is, well, a parallel algorithm. This is nothing actually useful. This is more like an exaggerated example of the kind of algorithms that are suited to be accelerated with FPGAs and thus with Hastlayer. This is a massively parallel algorithm, also called embarrassingly parallel. Because what it does is that here, there's a bit of logic. This just simulates that we are doing stuff. By the way, this code and all the other samples and the whole thing is up on GitHub. I will show you the link later. And this logic is executed in tasks. This code starts many tasks. You can think of tasks as kind of threads, but they are managed by the .NET framework. So there's no thread starvation, for example, but it's for multi-threading. And we start actually this many threads. This many is 280. We start 280 tasks threads here. Why 280? Because that many will fit on this device that I have here and this FPGA that I will use for the demonstration. Because these 280 tasks, when I run them on a CPU, like on the CPU of this device, they will run just on these cores that you have there. On my laptop, that would be 4 cores. On this device, it's 2 cores. But if you use Hastlayer to convert this into a hardware implementation, then you will get actually 280 little processing cores all working in parallel. You will get a hardware level parallelization of 280. And this many will fit because, of course, FPGAs are not limitless. This many resources are there on this particular device. And pretty much that's the algorithm. It does some stuff on 280 threads/tasks. sums together the outputs, and that's it. All right, let's now actually try this out. And I forgot to copy the script, so sorry about that. But let me open a serial shell to this device here. This is an FPGA board, a development board based on the Zynq family of devices, and that means that it has an ARM CPU coupled with an FPGA, and it runs Linux. So hence why I have a shell here. And what I'm doing here now is running a demo application. It will take a bit of time. We will see the results in a minute, like literally about a minute. What happens now is that first, that parallel algorithm will be executed as software, so on the ARM CPU of this device. By the way, this is a dual-core ARM CPU clocked at around 650 megahertz. Sorry about that. And once the software execution is finished, it will execute the same thing with Hastlayer on the FPGA part of the Zynq 3 times. This actually happens, so let's see the results. Let me scroll up a bit here. Okay, scrolling apparently doesn't work, so like here. And here's the results. Well, here's one of the results. On the CPU, it took around 25 seconds. Okay, so for 25 seconds, these 2 cores churned away. What happened to the hardware? If you scroll down here a bit, we will see the results of the first hardware execution. And that was about 330 milliseconds altogether. So it took 330 milliseconds from the start of sending the data from the CPU to the FPGA until we got the results back. So that was the total. Actually, so it was about 100 times faster, or 2 orders of magnitude faster. Now, if we only take the hardware execution into account, actually, then it was 240 milliseconds only. So this this round trip to the FPGA takes a lot of time, actually, but that diminishes if your algorithm takes a lot of time to compute. So while this was a synthetic example, I hope it provides a glimpse into what's possible with hardware acceleration. I will show you a couple of other results as well, because we have full support for the Vitis framework of the FPGA manufacturer called Xilinx. But this allows us is to target multiple devices, not just these devices, but also accelerator cards in data centers. The Alveo family of Xilinx is widely available in cloud providers. Those you can use as well. And also target aerospace applications, because this device here is actually the same thing that's widely available as as the onboard computer of new space satellites. So this little piece, actually not the whole thing, the actual device is just the little thing in the very middle. This is pretty much the same hardware that you can find on board of satellites and drones and robots. So with this, you can pretty much run exactly the same codes, both in the data center for example, image processing tasks when you process satellite imagery, and also the same code on board of a satellite to pre-process satellite imagery right there on board. A couple of results on the Alveo boards, so those FPGA boards that are available in cloud computing providers. We got speed ups somewhere from 4 times to 34 times, and the power efficiency increase was a bit better, something from 20 times to 120 times. Now the power efficiency translates not just into saved power, which is good for the environment, but also into cost savings, of course. On the Zynqs, so on these smaller devices, we got actually nicer results for some reason. The baseline there was the 24 times speed increase for image processing algorithms. These are just a couple of sample algorithms that you can see on GitHub, up to 100 times, and similar things with the power efficiency increase. And one thing that might be interesting for those people working on scientific computations here is a POSIT number format, The cool thing it has here, and with high-level tools like this, is that you can even implement your own number formats. And that's what we actually did. Well, we implemented a number format invented by a mathematician called Dr. John Gustafson. We pretty much created a .NET library, and with a flip of a switch, we created the corresponding hardware implementation with Hastlayer, which means that we now pretty much have a POSIT processor. And why POSITs are good is because they promise to offer better accuracy and better range with the same amount of bits than the IEEE standard floating point numbers. They're useful if you do some scientific computations. Pretty much that was it from me. If you like this, and I really hope you did, then please check out the SDK. It's up on GitHub, and be ready, because hopefully I would think that definitely you'll hear more from FPGA computations in the near future. So thank you very much, and I think we have a couple of minutes for questions if there are.
Thank you very much. It's really exciting to do everything in real time here. So thank you very much. And
a lot of cables there.
Yeah, a lot of cables at least. Okay, so questions. Please do speak up because of the outside people.
You mentioned image processing, and what's typical complexity of processing algorithms? So is it kernel convolution or neural network?
Sorry, could you speak up a bit? I have a bit of a hard time.
So you mentioned image processing as a use case. So what's the typical complexity of image processing algorithm that's implemented here? Is it just a kernel convolution or maybe neural network inference?
Should I repeat the question?
No, it would be very useful.
Okay, so the question was about what's the typical complexity of the image processing algorithms you can implement here. It's just some simpler image processing, or it's more complex like neural networks. The short answer is it depends. It depends on the capacity and the other capabilities of the device, what makes what's feasible. This is a relatively small device. So these data center accelerator cards I mentioned have a capacity 50 times more. On this device, I think it's useful to just do some simple kernel processing right away. One of the samples we use here is some contrast modifier logic, which is quite simple but highly parallelizable. There's no intelligence of sorts there. That being said, there are also FPGA optimized versions of machine learning libraries. We didn't do anything with that yet, but Xilinx, for example, offers some pre-baked libraries of that sort.
Further question? Matthew, please.
In the context of using FPGAs in space, which property of FPGAs is more important, the power efficiency or the reconfigurability?
So the question was, in space applications, which property of FPGAs is more important, power efficiency or reconfigurability, or perhaps performance? But I think that right now it's actually power efficiency. So we are talking about, when talking about these kinds of Zynq devices, we are talking about new space satellites, which are small and nano satellites, like the small CubeSats. That means that power is the biggest constraint, both electrical power that you get to run devices and both what you can dissipate as heat. That being said, also with new space, reconfigurability, and pretty much the ability to update everything on the software side on your satellite becomes more and more important. So I think that will be more important in the near future. Right now, power efficient side.
Any?
About number formats, so also sometimes people are limited cover. So do you have access to type of number formats like double precision, single precision? Is this all available? This hardware?
So I didn't quite understand the first part of the question. Probably.
Precision, is it available both formats on the hardware or
So the question was whether single or double precision floating point is available. Not with Hastlayer. Generally, it's possible with FPGAs. I mean, in principle, it is also possible with Hastlayer, but it's not really efficient. Implementing any kind of floating points, also posits on FPGAs, is costly. It's also costly in CPUs. We just don't know about it. When it's about FPGA computations, we prefer not to do any floating points, just integer and especially bit computations. But you can implement it in a soft way, like with posits. That's the only way to do that on this device actually. But there are certain devices that have hard floating point cores as well. There, if you use the manufacturer's libraries, you can get direct support.
Okay, time is running, so Zoli will be here for the rest of the day, I think.
Yeah, until lunch.
Until lunch.
Until the end of lunch.
So I would have a couple of interesting questions, but thank you very much again for you.
Thank you.
And,